Hi students, in the last video we left off with relative frequency definition of probability. Though the definition was intuitively appealing, we realized some problems. One of the problem is performing random experiment a large number of times to compute the probability, which may not be feasible. And also, this definition is not going to be suitable for developing mathematical theory of probability. Okay, that's why we are not going to start with this one. But we are going to observe three essential properties of chance or probability from the relative frequency. The one is non-negativity property. For any event, according to relative frequency definition, the probability of event defined as limit of the relative frequency. The relative frequency always non-negative. So limit of non-negative going to be non-negative. That's why the probability of any event going to be non-negative according to relative frequency definition. That's the one property. Next one is something called certainty property. Probability of omega. Omega is sample space consisting of all possible outcomes, which is itself an event. We know that omega is always event because every sigma field should contain omega itself, right? Okay. Now this omega is called sure event because it always happens. Whenever we perform a random experiment, it results in some outcome, that some outcome sitting in sample space. So the sure event, this omega always happens. That's why we call it sure event. The probability of sure event is going to be limit of the relative frequency of the sure event here. Here the numerator is frequency of omega. Out of n trial, omega happen in n times, right? So this fraction going to be n by n, which is 1. Okay, so that's why the limit of the constant 1 going to be 1. So the probability of sure event going to be 1 according to relative frequency definition. This is something called certainty property. Next, third one going to be something called additive property. If you take two events E1 and E2 which do not happen simultaneously, that means E1 intersection E2 empty means they do not have a common outcome. So whenever, which means E1 E2 do not happen simultaneously. At most one event can happen. Okay, then the probability of E1 union E2 according to relative frequency definition, limit of relative frequency of E1 union E2. Here the numerator is frequency of E1 union E2. That means number of times E1 or E2 happen in n trials. Since E1 E2 do not overlap, according to some rule, it should be number of times E1 happen plus number of times E2 happen in n trials. So this is going to be frequency of E1 plus frequency of E2 by n. Now if you separate, then it's going to be limit of relative frequency of E1 plus limit of relative frequency of E2. Again, from the relative frequency definition, this is precisely probability of E1, this is precisely probability of E2. So the probability of E1 union E2 going to be probability of E1 plus probability of E2, which is something called additive property. Okay. Now we are going to give axiomatic definition of probability, including these three properties as axioms. Okay. In fact, we are going to need a more stronger version of the third property, something called countable additivity. Not just for two events or finitely many events. Whenever we have E1, E2, so on, En, countable collection of events in which no two happen simultaneously, that means E intersection Ej equal to Mt for I not equal J, then the probability of their union, countable union, should be sum of their probabilities. We want this one because whenever we have a sample space which is infinite, so this third property is not going to be enough, so that's why we need a stronger version of that property third, something called countable additivity. Okay, fine. Next I'm going to give axiomatic definition of probability. Axiomatic definition of probability. Let omega comma script f is let omega script f be a measurable space. Here omega is the sample space, script f is the sigma field of event space. We call it measurable space. A set function p from event space to real numbers is called probability measure or probability function on the measurable space omega comma script f if it satisfies the following three axioms. See, set function simply means a function whose domain is set of sets, because with the domain here script f, right? Event space. Event space elements are again sets, events, right? That's why we call set function. Okay. So the probability function going to be, or probability measure going to be set function from event space to R. It's the rule of assigning numbers to events, okay, which satisfying three axioms. Axiom 1 is non-negativity axiom. For every event, the probability of E should be non-negative. So this function should take non-negative values for any event. Okay, that is the axiom 1. Axiom 2 is certainty axiom. For a sure event, we should be able to assign 1. For probability of omega should be 1. This is axiom 2. Axiom 3 is for any countable collection of events, E1, E2, so on, En in script f, okay, where Ei intersection Ej equal to empty for I not equal j, which means no two events in this collection happen simultaneously. Okay, so that means at most one event can happen. Such a collection also called mutually exclusive collection or pairwise disjoint collection. Okay. Then the probability of their countable union going to be sum of their probabilities. Probability of union I equal to 1 to infinity ei going to be summation I equal to 1 to infinity probability of ei. This is called countable additivity axiom. Any function from event space to R satisfying these three axioms is called probability function. Simply, probability is a rule of assigning numbers to events satisfying these three axioms. Okay, fine. So now we have three components. For a random experiment, we have a sample space and a collection of events of interest sigma field script f, and we have a probability function on the measurable space omega comma script f. Then this triple is called probability space, or you can call probability model. Okay, fine. We are going to call this triple omega event space and probability function. This triple is called probability space or probability model. Now let me define few things here. Let capital I be an index set, any set where indices vary. A collection of events ei where small I varying over capital I index set in script f set to be mutually exclusive if ei intersection ej equal to empty for I not equal j. Which means no two events in the collection can happen simultaneously. Which also means whenever we perform an experiment, at most one event can happen. Okay, such a collection of events are said to be mutually exclusive collection. Next, the collection of events ei in script f said to be exhaustive collection if they cover all sample space, which means when I take their union, I should get all sample space. Means every outcome is covered by some event ei. Which also means whenever we perform an experiment, at least one event will happen in the collection. Okay, such a collection is said to be exhaustive collection. Next, The collection of events ei in script f said to form a partition for omega if they are both mutually exclusive and exhaustive. That means whenever we perform an experiment, exactly one event in the collection always happens. Exactly, not more, not less. Exactly one event in the collection always happens. Such a collection is said to form a partition for omega. The whole omega are divided into parts, E1, E2, they are going to be non-overlapping parts which cover all sample space omega. Such a collection is said to form a partition for omega. Okay. Next. In the following theorems, we are going to prove the underlying probability space is going to be this: omega, script f, and the probability function p. Okay. So I'm not going to mention every time this triple. So just let's assume that underlying probability space always this for all the statements I'm going to make. The theorem 1. The probability of empty event, which is also called impossible event because it has no outcome, it will never happen, right? Okay, so intuitively we feel that the probability of this impossible event must be 0, but we are not demanding it from the definition. Okay, but this will actually follow from axiom 1, 2, 3. Okay, let's prove it. Proof: take event to be sure event omega whole sample space and ei equal to impossible event ei empty event from 2, 3, 4, so on. That means E2, E3, E4, so on. Everything is empty event pi and E1 is omega. Then this collection E1, E2, E3 and so on, this countable collection going to form a mutually exclusive collection, right? Also, they are going to form a partition because E1 itself cover all omega, right? That's why we have omega equal to union I equal to 1 to infinity ei because E1 itself cover all omega, and also ei intersection ej equal to mt for I naught equal j because at least one of the ei comma ej will be empty, so intersection going to be empty always for I naught equal j. Okay, so now the probability of omega going to be the probability of union I equal to 1 to infinity ei. Okay, and here E1, E2, so on, En mutually exclusive collection. Okay, now I can apply axiom 3 for the right hand side. The probability of this union of this countable collection going to be sum of their probabilities. That's why I'm writing the probability of E1 plus probability of E2 plus probability of E3 plus so on by axiom 3. Okay. Now the E1 is nothing but omega and E2 is nothing but pi, E3 is nothing but pi and so on. And now from axiom 2, the probability of omega is going to be 1. So this is 1. So these two cancel. Now we end up with the probability of pi plus probability of pi plus probability of phi so on. This is equal to 0. Okay. Now, and also from axiom 1, the probabilities are always non-negative. So this is non-negative, 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 so on. Sum of the non-negative terms 0 means each term must be 0, right? That implies we must have the probability of the pi should be 0. Then only the sum can be 0. Okay, that's why. So we must have the probability of impossible event must be 0. Okay, it actually follows from axiom 1, 2, 3. We don't have to include as a property, we don't have to demand in the definition. Okay, fine. Next one, finite additivity, which is a weaker form of axiom 3, so it should be true. We'll prove it anyway. Here we have a finite collection of mutually exclusive events. Here E1, E2, En are events such that Ei intersection Ej equal to empty for I not equal j. Then we have to show that the probability of union I equal to 1 to n Ei equal to summation I equal to 1 to n probability of A, which is a finite additivity property. Okay. Here idea is to extend the given finite collection of mutually exclusive events to countable collection of mutually exclusive event so that we can apply axiom 3. Okay, so let's take En plus I equal to empty event for I equal to 1, 2, 3, so on. That means En plus 1, En plus 2, En plus 3, all these events we are taking as empty events, okay, empty sets. Then we have a new collection E1, E2, so on, En, En plus 1, En plus 2, and so on. Okay, we have a countable collection of events. These are still going to be mutually exclusive because Ei intersection Ej is going to be empty for I not equal j. Because if I and j coming from 1 to n, anyway we have this, so Ei intersection Ej should be empty for I not equal j. If one of I and j coming from outside 1 to n, and we know that from n plus 1 onwards all are empty event, so intersection with the empty event will be anyway empty. So we have this. Now here this countable union I equal to 1 to infinity I will still be same as this finite union I equal to 1 to an I, because from n plus 1 onwards all events are empty. These empty events will not contribute anything to union because they have nothing. Okay, so now the probability of the left hand side will be same as probability of the right hand side, but this E1, E2, so on, En, this is a countable collection of mutually exclusive event. So the right hand side I can apply axiom 3. So this is going to be sum of the probabilities summation I equal to 1 to infinity the probability of Ei by axiom 3. Okay. Now let us break the summation into two parts, from I equal to 1 to n, from n plus 1 to infinity, like this. Now the right hand side equal to summation I equal to 1 to n probability of Ei plus summation I equal to n plus 1 to probability of Ei. From n plus 1 onwards each Ei going to be empty, right? Let's replace that. Okay, this Ei is empty from n plus 1 to infinity. But the probability of empty event is 0 from theorem 1. All the summation going to be 0. So therefore we end up with the probability of union I equal to 1 to n Ei equal to summation I equal to 1 to n probability of Ei. Okay, this is something called finite additivity property. Okay, fine. So let's clear this. So here we have this. The probability of union I equal to 1 to n Ei going to be summation I equal to 1 to n probability of Ei whenever E1, E2, En are mutually exclusive events. Okay, this is the finite additivity property. Theorem 3. For any event in event space, the probability of E complement equal to 1 minus probability of E. Okay, it's very easy to prove. Let's prove it. Proof. First of all, we can see that for any event E in event space, E union E complement equal to all sample space omega. So if we take probability both sides, probability of E union E complement equal to probability of omega. Now, and E complement are mutually exclusive, so I can apply finite additivity left hand side, and the probability of omega equal to 1 from axiom 2. So if you do that, probability of E union E complement, I can write probability of E plus probability of E complement, and probability of omega we can write 1 from axiom 2. This left hand side follow from finite additivity because of E intersection E complement is empty. E complement always mutually exclusive, right? They do not have anything common. They never happen simultaneously. Okay, so therefore we have this. The probability of E complement equal to 1 minus probability of E. Okay, fine. Next. Theorem 4. For any two events E1, E2 in event space, we have this. Probability of E1 intersection E2 complement equal to probability of E1 minus probability of E1 intersection E2. See, this E1 intersection E2 complement can also be written like this. E1 minus E2. That means outcomes in E1 but not in E2. Okay. So that means probability of E1 minus E2 equal to probability of E1 minus probability of E1 intersection E2. Okay, let's prove this. Proof. Look at this Venn diagram here. This rectangle area is all sample space omega. Here E1 is covered in one circle, E2 is covered in one circle. They overlap like this. Okay. Now you see the green portion consisting of outcomes in E1 but not in E2. And the brown portion is outcomes in E1 and E2. So the whole E1 is made of green portion and brown portion. So I can write this E1 equal to the green portion, which is E1 intersection E2 complement, union the brown portion, which is E1 intersection E2. And I can also see that these two events, E1 intersection E2 complement and E1 intersection E2, these two are mutually exclusive because I can see from the Venn diagram they don't overlap, they don't have anything common. So now if I take the probability both sides, the probability of E1 equal to the probability of E1 intersection E2 complement union E1 intersection E2. Now I can apply finite additivity right hand side because these two events are mutually exclusive. Okay. Now, okay, after applying finite additivity right hand side, we have probability of E1 equal to probability of E1 intersection E2 complement plus probability of E1 intersection E2. Now you take this one other side and you'll end up with this. Probability of E1 intersection E2 complement equal to probability of E1 minus probability of E1 intersection E2. Okay, this is the result. Okay, you can also write like this: probability of E1 minus E2 equal to probability of E1 minus probability of E1 intersection E2. Okay, fine. This is the result. Next, corollary 1. If E2 is subset of E1, then probability of E1 intersection E2 complement equal to probability of E1 minus probability of E2. I can also write like this: probability of E1 minus E2 equal to probability of E1 minus probability of E2 whenever E2 is subset of E1. See, here E2 subset of E1 means all outcomes in E2 also in E1, which means whenever E2 happen, E1 also happen. That is the meaning of E2 is subset of E1. Okay. It's actually follow from previous theorem. Probability of E1 intersection E2 complement, from the previous theorem I can write probability of E1 minus probability of E1 intersection E2. But E2 is subset of E1, right? So we have this E1 intersection E2 going to be equal to E2. Therefore, the probability of E1 minus this E1 intersection E2, I can write E2. Okay, therefore the probability of E1 intersection E2 complement equal to this one. Okay, this is the result. Corollary 1. Next. Corollary 2, monotone property. Here is the statement. If E2 is subset of E1, then probability of E2 less than or equal to probability of E1. Let's try to understand the meaning of the statement intuitively. E2 is subset of E1 means whenever E2 happened, E1 also happened, which means we should have more chances for E1, right? That's what it says. The probability of E2 should be less than or equal to probability of E1. Okay. Now let's prove it. It's actually follow from corollary 1. From corollary 1, whenever we have a E2 subset of E1, we know that the probability of E1 intersection E2 complement equal to probability of E1 minus probability of E2. But the probability of any event always non-negative by axiom 1. So we have this is non-negative. Therefore, I can write the probability of E1 minus probability of E2 is always non-negative. So that will give you this one. The probability of E2 less than or equal to probability of E1. Okay. This is something called monotone property of probability. Okay. If E2 is subset of E1, then probability of E2 will be less than or equal to probability of E1. Okay. Fine. Next. Theorem 5. For any event E in event space, 0 less than or equal to probability of E less than or equal to 1. That means for any event, the probability of event must be between 0 and 1. That was our goal actually. For every event, we want to assign a number between 0 and 1, which measures the likelihood of that event to happen, right? But in the definition, we never said this. In the definition, we simply said the probability is a function from event space to real numbers. Axiom 1 only says that it's a non-negative real number, but we are never saying that it's actually between 0 and 1. But this actually follows from axiom 1, 2 and 3 and the previous results which are proved using the axiom 1, 2, 3, right? Now, for any event E having this relation with empty set and all sample space omega, okay? So, empty set pi subset of E subset of omega. This is always true for any event, right? Now, if you take the probability, then the probability of empty set less than or equal to probability of E less than or equal to probability of omega because of monotone property we just proved. Okay. Now we know that the probability of empty set is 0 from theorem 1. The probability of omega is 1 from axiom 2. So we have this. The probability of E actually between 0 and 1. 0 less than or equal to probability of E less than or equal to 1. Always for any event. Okay. So fine. Next. Equally likely events. If E1, E2, so on, Ek are events in event space script f which form a partition for sample space omega. That is, here E1, E2, so on, Ek are mutually exclusive and exhaustive events. And random experiment is of such a character that we don't prefer one event over other. That is, it is reasonable to assume that each of E1, E2, so on, Ek has same probability of occurrence. Then we say events E1, E2, so on, Ek are equally likely. Let me give some examples. In a random experiment of picking a number from this whole number set 0, 1, 2, so on, sample space will be again 0, 1, 2, 3, so on. Okay. Let's fix n. Let me make a n events here like this. Fix n. Let me make event ei consisting of all numbers for which n divides k minus I, for I equal to 0, 1, 2, so on, n minus 1. That means E0, E1, E2, so on, En minus 1. Let me show you what are these events. Here E0 will consist of all whole numbers 0, n, 2n, 3n and so on. E1 will consist of all whole numbers 1, n plus 1, 2n plus 1, 3n plus 1 and so on. E2 will consist of all whole numbers 2, n plus 2, 2n plus 2, 3n plus 2 and so on. Ei will consist of I, n plus I, 2n plus I, 3n plus I and so on. Okay, for I equal to 0, 1, 2, so on, n minus 1. You can see that Ei consists of all numbers which leaves the remainder I when you divide by n. Okay, so you can easily observe that if you take the union of these n events, you will get whole sample space, because take any number divide by n, it will leave the remainder between 0 to n minus 1. Okay, so it will fall into one of the event here. Also, ei intersection ej going to be empty for I not equal j. It's easy to see. So they form a partition. E0, E1, E2, so on, En minus 1 form a partition for whole omega. Also, here we feel like we don't prefer one event over other. Here it is reasonable to assume that each event has a same probability of occurrence. Okay, that's why it is reasonable to assume that E0, E1, so on, En minus 1 are equally likely events in this case. Okay, let me give another example. In a random experiment of picking a card from well-shuffled pack of 52 cards, these are the 4 events I am going to consider. E spade is the event of getting spade card. E club is the event of getting clubs card. E heart is the event of getting heart cards. E diamond is the event of getting diamond card. Okay, so one can easily verify that they form a partition for whole sample space omega, and as each event will consisting of 13 cards. Okay, so we can't prefer one event over other, so it is reasonable to assume that each event having same probability of occurrence. So we want to say these 4 events are equally likely events. Okay, next, theorem 6. If E1, E2, so on, En are equally likely events in event space, then the probability of Ei must be equal to 1 by n. We know that equally likely event should have a same probability, but that same probability must be equal to 1 by n if there are n equally likely events. Okay, let's prove this. Proof. Here E1, E2, so on, En are equally likely events. That means they form a partition, right? Partition means they cover all sample space and they are mutually exclusive. That means no two can happen simultaneously. Okay, Ei intersection Ej equal to empty for I not equal j. Also, each event should have a same probability of occurrence. That same probability I am taking A. A is something between 0 and 1. Okay, fine. Now, if I apply probability to this both sides, the probability of union I equal to 1 to n Ei will be same as probability of omega. Now, the right hand side, from axiom 2 I'll write 1. The left hand side we can apply finite additivity, because E1, E2, so on, En also mutually exclusive because they form a partition. So I can write the left hand side is equal to summation I equal to 1 to n probability of Ei because of finite additivity. The right hand side is equal to 1 because of axiom 2. This is from finite additivity, this is from axiom 2. Okay, fine. In the next step, I can replace this probability of Ei with this A. Okay, so now summation I equal to 1 to n, the probability of Ei going to be same A for I equal to 1 to n. So if I write that, then the left hand side will be NA, this will be NA equal to 1, that will give A equal to 1 by N. So therefore, what is the probability of EI? That equal to 1 by N. We know that equally likely means we should have a same probability of occurrence for each event, but now I am saying that that same must be equal to 1 by N when you have n equally likely events like this. Okay, fine. Next, corollary. In a probability space omega script f and p, if omega is finite and outcomes are equally likely, then for any event E in event space, the probability of E going to be simply the number of elements in E by number of elements in omega. Okay. Okay. Here omega is finite, means total possible outcomes are finite and outcomes are equally likely. Outcomes are equally likely means singleton events, they are also called elementary events. Elementary events are equally likely. Okay. So, okay, now let omega consisting of n outcomes like this. Okay, small omega 1, small omega 2, small omega n, like this. And let me take ei equal to singleton omega I, small omega I, okay, which are also called elementary events. Singleton events are also called elementary events. Okay, now here outcomes are equally likely means these elementary events are equally likely. So here E1, E2, so on, En are equally likely. Okay, from previous theorem I can say that, okay, here E1, E2, En are equally likely. So from previous theorem I can write the probability of Ei equal to 1 by N for all I equal to 1 to N. Okay, what is Ei? The singleton omega I. Fine. Now if you take any event in event space, that event will consist of some outcome from the sample space. Here sample space consisting of omega 1, omega 2, so on, omega n. Then E will consisting of some outcomes. So now let me describe E like this. E consisting of small omega I1, small omega I2 and small omega IR. There are R outcomes, so the number of elements in E is R. Here I1, I2, IR, some candidate from 1 to N. Okay. Okay, that means I have some outcome from omega that I am describing like this. Okay, now this E can be expressed like this. In and of these elementary events for k equal to 1 to R, EIK. See, this EIK is a event consisting of single outcome omega IK, right? That's why I can express like this. Now, the singleton events are always going to be mutually exclusive because they cannot have anything common, right? Now, the probability of E I can write the probability of union k equal to 1 to R EIK. Here I can apply finite additivity. Okay, so this is going to be summation k equal to 1 to R probability of EIK, and we just realized that the probability of any event must be equal to 1 by n. So each equal to 1 by n here, summation k equal to 1 to R 1 by n. So this sum add up to R by n, where R is size of E, n is size of omega. Okay, therefore probability of E equal to number of elements in E by number of elements in omega. This also referred as classical definition of probability. Okay, this way of computing probability makes sense only when omega is finite and outcomes are equally likely. If you want to use this, you must have used a lot in PUC, all problems, but you should know that you can use this tool to compute probability only when sample space finite and outcomes are equally likely, because whether you are using axiomatic definition or this one, both mean same thing in that case. Okay, fine. Next, theorem 7, addition theorem of probability. For any two events E1, E2 in event space, probability of E1 union E2 going to be probability of E1 plus probability of E2 minus probability of E1 intersection E2. Okay, so this is how you deal with the probability of E1 union E2 in general. Okay, because we can't simply write probability of E1 plus probability of E2 unless we know E1 and E2 are mutually exclusive by additivity, right? So this is a general result when you don't know anything about E1 and E2. Fine, let's prove this. So look at this Venn diagram here. This whole rectangle is the sample space omega. Here this E1 union E2 covered in green and red portion. Okay, this green portion actually E1 intersection E2 complement, because outcomes in E1 but not in E2. So red portion precisely E2. Okay, the whole E1 union E2 we can express like this: E1 intersection E2 complement union E2. The good thing about writing E1 union E2 like this is, here these two are going to be mutually exclusive. So when we try to compute the probability, we can apply additivity. Okay, that's the good thing about writing E1 union E2 like this. Okay, now if you try to compute the probability for left hand side, it's going to be same as for probability of the right hand side. Now here these two are going to be mutually exclusive. Okay, E1 intersection E2 complement, E2 are mutually exclusive, as we can see from Venn diagram. They don't have any overlapping. Okay, fine. Now if we apply additivity, then this I can write probability of E1 intersection E2 complement plus probability of E2 because of additive property. Now from theorem 4, this can be replaced with probability of E1 minus probability of E1 intersection E2. Let's do that. So this part is replaced with this probability of E1 minus probability of E1 intersection E2 because of theorem 4. Okay, so done. So therefore the probability of E1 union E2 equal to probability of E1 plus probability of E2 minus probability of E1 intersection E2. This is the addition theorem for two events. Next, corollary for three events also we can have addition theorem. Okay, if E1, E2, E3 are three events in event space, then probability of E1 union E2 union E3 going to be probability of E1 plus probability of E2 plus probability of E3 minus probability of E1 intersection E2 minus probability of E2 intersection E3 minus probability of E1 intersection E3 plus probability of E1 intersection E2 intersection E3. This is the addition theorem for three events. Let's do using the previous theorem. Okay, it actually follows from previous theorem. So what we do, the E1 union E2 union E3 we are going to see as E1 union E2 union E3, union of two events. Okay, now let's apply addition theorem for two events for E1 and E2 union E3. Then we will write this probability of E1 plus probability of E2 union E3 minus probability of E1 intersection E2 union E3. So if you apply distributive laws for this, we can write this E1 intersection E2 union E1 intersection E3. Okay, now again let's apply addition theorem for two events here and here. Okay, here we have a E2 union E3, here we have a E1 intersection E2 union E1 intersection E3. Let's apply for these two cases. The probability of E1 as it is I wrote. So the probability of E2 union E3 I am replacing with addition theorem of probability for E2 and E3. Probability of E2 plus probability of E3 minus probability of E2 intersection E3 minus here the addition theorem for these two events E1 intersection E2 E1 intersection E3. So the probability of E1 intersection E2 plus probability of E1 intersection E3 minus probability of E1 intersection E2 intersection E1 intersection E3 going to be simply E1 intersection E2 intersection E3. So after multiplying minus, we simply get this. Okay, so this is addition theorem for probability for three events. Okay, now we can generalize for n events. So this is called inclusion exclusion principle. For any events E1, E2, so on, En in event space, the probability of E1 union E2 union En going to be this, which is exactly looking like inclusion exclusion principle of counting. The only difference is the number of elements replaced by probability P, right? So It's not hard to remember if you remember inclusion exclusion principle of counting. So it is same. Here you can prove it by induction using base case n equal to. Okay. Next. Problem 1. Problem 1. If 4 married couple are seated at random around round table, compute the probability that no wife sit next to her husband. Okay. Here our outcomes are going to be circular arrangements of 8 people, right? Here our sample space omega consisting of all circular arrangements of 8 people. So therefore the number of elements in omega are going to be 8 minus 1 factorial, which is 7 factorial. Here sample space is finite, and we can also assume that outcomes are equally likely as people are sitting at random. Okay. Let EI denote the event that ith couple sitting together for I equal to 1, 2, 3, 4. Then EI complement will denote the event that ith couple not sitting together. What is our event of interest? Our event of interest is no wife sit next to her husband. Means simply no couple sitting together. So our event of interest can be expressed in terms of E1, E2, E3, E4 as follows. Intersection I equal to 1 to 4, EI complement will denote no couple sitting together. Okay. So now therefore we are interested in this probability, right? Using De Morgan laws, I can write I equal to 1 to 4 EI complement as union I equal to 1 to 4 EI whole complement. So the probability of this going to be probability of this is equal to 1 minus the probability of union I equal to 1 to 4 EI. Okay. So therefore the probability of intersection I equal to 1 to 4 EI complement equal to 1 minus probability of union I equal to 1 to 4 EI. Here we replace this with the inclusion exclusion formula. This is from inclusion exclusion formula for this one, right? Now we are going to compute the probability of EI intersection EJ, probability of EI intersection EJ intersection EK, and probability of E1 intersection E2 intersection E3 intersection E4. Then we plug it here, then we get the required probability. Okay. Now to compute the probability of EI, let's look at the size of the EI. So EI is the event which consisting of all outcomes in which ith couple sitting together. To count this, our idea is to tie ith couple, which can be done 2 factorial ways. Once you tie them, you treat them as a single person. Now 1 plus remaining 6 people, so there are total 7 people. You can arrange them in a circular fashion in 7 minus 1 factorial ways. That's why the 6 factorial. So 2 factorial into 6 factorial. So the number of elements in EI is going to be 2 factorial into 6 factorial. Therefore, the probability of EI, the number of elements in EI by number of elements in omega. That's why it's going to be 2 factorial times 6 factorial by 7 factorial. So this gets simplified to 30 by 105 for any I between 1 to 4. Same. Okay. Now the number of elements in EI intersection EJ. That means arrangements in which ith couple sitting together and jth couple sitting together. Okay. To count them, what we do, we tie ith couple and jth couple. Ith couple can be tied in 2 factorial ways. Jth couple also can be tied in 2 factorial ways. Those two couple can be tied in 2 factorial square ways. Then you can treat these two couple as a single person. 1 plus 1, 2, and remaining 4 people. So total 6 people you are arranging in circular fashion. That can be done in 5 factorial ways. That's why the probability of EI intersection EJ is going to be 2 factorial square times 5 factorial by 7 factorial, which gets simplified to 10 by 105 for any 1 less than or equal to I less than j less than or equal to 4. Similarly, the number of elements in EI intersection EJ intersection EK is going to be 2 factorial cube times 4 factorial. The probability is going to be 2 factorial cube into 4 factorial by 7 factorial, which gets simplified to 4 by 105 for any I less than j less than k between 1 to 4. Now number of elements in E1 intersection, E2 intersection, E3 intersection, E4. Arrangements in which all couples sitting together. So you can tie the 4 couple in 2 factorial to the power of 4 ways. Then you treat them as a single person. Then you have a 4 people which they can be arranged in 4 minus 1 factorial ways, which is 3 factorial. Then the probability going to be 2 factorial to the power of 4 into 3 factorial by 7 factorial. This gets simplified to 2 by 105. Now we got all the probabilities that are required in principle of inclusion-exclusion formula. Now we go ahead and plug it in the previous expression. Okay. Now in the expression for probability of intersection I equal to 1 to 4 EI complement, the probability of EI is got replaced by 30 by 105. Probability of EI intersection EJ got replaced by 10 by 105. Probability of EI intersection EK got replaced by 4 by 105. And probability of E1 intersection E2 intersection E3 intersection E4 we replace with 2 by 105. Okay, now we know that in the summation there will be 4 choose 1 terms. In the summation there will be 4 choose 2 terms. In the summation there will be 4 choose 3 terms. There is only one term, so that we can, next step we can write 1 minus of 4 choose 1 times 30 by 105 minus 4 choose 2 times 10 by 105 plus 4 choose 3 times 4 by 105 minus 2 by 105. So whole thing gets simplified to 0.295. Okay, just feel free to verify this. Therefore, the probability of no wife sit next to her husband equal to 0.295. Okay, fine. Problem 2. A bowl contains 16 chips, of which 6 are red, 7 are white, 3 are blue. If 4 chips are taken at random without replacement, find the probability that question A, each of the 4 chip is red. Question B, none of the chip is red. Question C, there is at least 1 chip of each color. Okay. Here 4 chips are drawn without replacement. So the sample space size will be 16 choose 4. Okay. So whose value going to be 1820. Okay. A. Let capital A denote the event that each of the 4 drawn chip is red. Okay, so all 4 should come from red chips. So the number of elements in A going to be, see here, out of 6 red we are choosing 4, and out of 7 white we are choosing 0, out of 3 blue we are choosing 0. All 4 chips are coming from 6 red. So this is nothing but 6 choose 4, whose value going to be 15. So now the probability of A going to be number of elements in A by number of elements in omega, which is 15 by 1820, whose value is 0.00824. Okay, next. B. Let capital B denote the event that none of the chip is red. So all 4 coming from non-red. So non-red how many? 7 plus 3, right? So we have to pick 4 chips from 7 plus 3 chips. So that's why the number of elements in B going to be, from 6 red we are picking 0, from remaining 7 plus 3 we are picking 4. So this can be done in 10 choose 4 ways, whose value is 210. So the probability of B going to be number of elements in B by number of elements in omega, which is 210 by 1820, whose value approximately 0.1153. So the probability of B going to be 0.1153. Okay. Next, question C. See, here capital C denote the event that at least 1 chip of each color. So this can happen one of the 3 ways. We may have a 2 red, 1 white, 1 blue, or 1 red, 2 white, 1 blue, or 1 red, 1 white, 2 blue, right? So that's why the number of elements in C going to be, we may choose 1 red out of the 6 red, 1 white out of the 7 white, and 2 blue out of the 3 blue. Or it may happen 1 red out of the 6 red, 2 white out of the 7 white, and 1 blue out of the 3 blue. Or it may happen 2 red out of the 6 red, 1 white out of the 7 white, 1 blue out of the 3 blue. Okay, so by some rule we can add this up, so you will get 819. So therefore the probability of C going to be number of elements in C by number of elements in omega, which is going to be 819 by 1820, whose value approximately 0.45. So the probability of C going to be 0.45. Okay, we will stop now. Thank you.